Hello, wherever you are watching this video, hopefully you've been reviewing for Organic Chemistry 8B, and hopefully you've been remembering some of the things that you've been taught in 8A. One of the most important things that you hopefully have been taught and taught well is that resonance is something that is very, very important. In 8A, there was pretty sure there's a whole chapter dedicated to it, and you kind of have to nail this resonance because if you don't, then later on down the line, there are going to be some reactions that involve having a component of resonance. So if you can't do those, then you can't do the reactions, obviously. So let's talk about resonance. Yeah. So all resonance is just electrons that are moving around within the structure of a molecule. That is the most basic explanation that I can give for you. So, for example, I'm sure you guys have seen this in organic chemistry 8A, where you have a classic benzene, and the benzene, right, these electrons that are in bonds right here, will move around. For example, right, they can move onto here, and they can form this structure right here. Now, to kind of break down what I just did here, right? We started off with these electrons that are kind of here, right, in the structure of a benzene, and we just moved them onto this carbon right here. Simple enough, yes? So the interesting thing about resonance is that whenever you see a structure drawn like this, or just any chemical structure in organic chemistry or in chemistry as general, it looks like the molecule is still. Yes, it looks like the electrons are fixed in one place. It looks like this electron is fixed to this bond right here. It looks like this electron is fixed in this position right here. And while technically that's easier for us to kind of see, it's not really entirely true. Electrons are constantly bouncing around the molecule, right? And the way that I like to compare this is that imagine if you ever seen like one of those flip books where somebody draws a picture onto a single page and then they draw another picture onto the next page, and then they kind of flip through the book, and it makes it look like there's an image that's moving, or like old school animators, right? When you're drawing, Mickey Mouse and I think it was called Willy Boat or something like that. How animators basically operate. Yeah, you draw one picture, and then you draw another picture of another object in a different position, and you just switch back and forth between those to give the illusion of motion on a screen. That's how I would kind of compare resonance. Yeah. So in reality, right, instead of having this benzene that's kind of just here, static, what actually is happening, right, is that we say for 1 second, right, this bond could be here, or this bond could be here, this bond could be here. And in reality, right, it looks like this. This kind of dots around the molecule is kind of how we illustrate that these bonds are constantly in motion. Now, obviously, it'd be really, really difficult for us to be able to know where exactly the electrons in a bond are at any time. I'm pretty sure, in fact, it's impossible. But for the sake of simplicity, right, if we took a snapshot of one of these, right, it would look like this. And so with that basic logic, resonance is just you flipping through frames of an animation of electron bonds that are moving around a molecule. And every single one of those frames is important because sometimes in some quote unquote frames, the molecule can be prone to certain types of chemical activity. That's why it's so important. And so we're going to take a couple of seconds, or a couple of minutes, hopefully, to kind of look at resonance and see what we can remember and make sure that you are able to understand and able to do resonance. So first things first, right? Going down to these two right here. The basic one of the two basic patterns of resonance is either you start with a plus charge or you start with a negative charge. And for plus charges, right, if you start off with a plus charge, it's pretty simple. So hopefully everybody here understands that when you have a plus charge and have a negative charge, those negative charges and those plus charges are going to basically attract each other, opposites attract, right? And so if you have a positive charge here that is fixed onto this carbon, what's going to happen is that you're going to, first structure you can draw is this. Yeah. The arrow represents, I'll write this in red, it's pretty important. Arrow represents two electrons moving. Yeah. And when you do that, this arrow right here is to show the transition between resonance structures. This bond moves on here. You see this? This bond went from here to here. Okay. Now, the important thing about resonance structures is that you have to make sure that you conserve any charges wherever you see them. And so we started off with a plus charge here. Did that plus charge disappear? Well, not really. It moved on to here. I'll let you take a sec. Let's take a second to analyze this, right? So this carbon right here had was neutrally charged because it had four things attached to it. One, two, three, and it had a fourth H right here. So this is neutral. That makes sense. Yes. However, this guy over here is plus charge. It has three things attached to it. One, two, and probably an H here. And so therefore it has a plus charge. If you're confused about this, go see my other video about formal charges. But you take this bond right here, you move this onto here, and you end up moving the plus charge from here to here. That makes sense, right? Because now this carbon right here that was originally neutral, right? The bond that was keeping this carbon neutral has moved on to here. And now you have this plus charge right here. Yeah. Hopefully that's starting to make sense to you. And then from there, we could draw another additional resonance structure. I'll move that onto there. We'll continue the pattern all the way down. Ooh, hopefully it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Cool. And that plus charge moves onto here. Same logic. Now, this is what I like to call major resonance pattern 1. I would say nearly 90 to 95% of all of the major resonance that you're going to be doing is going to either start off with a plus charge or negative charge. And this is the first of these patterns. And so whenever you have a plus charge, usually it's pretty simple. You just move a bond around, and that's pretty chill for the most part. That's one of the easier ones. And then you have major resonance pattern 2. Yeah. This one's a little different because you start off with a negative charge. Yeah. So what type of patterns can we draw from this? Well, negative charges, right? Well, you're obviously not going to be moving any of these charges, or any of these bonds onto here, because if you did, what would happen? Pause the video, explain it to yourself out loud. But what would essentially happen is that if we did this, if we did the same thing as major resonance pattern 1, what's going to happen is that, well, how many things are going to be attached to this carbon that's right here? How many things are going to be attached to there? So let's count. How many electrons are going to be surrounding that carbon? If you remember anything about the octet rule, you remember that the total amount of electrons, both in the bonds and in lone pairs that are surrounding any atom, can't be higher than 8 exactly. Can't be higher, can't be lower. Has to be 8. And so if we did this, that means 1, 2, 3, 4, 5, 6, 7, 8. And oh, yes, I confused myself for a second, but yes, there's also an H here in the back that's attached. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so that's 10 electrons that are surrounding this atom. That's a no-go. All right. So if we did this, there'd be 10 electrons. That would violate the octet rule. So this is obviously no-go. We can't do this pattern. So if that's the case, then how do we do this correctly? Let's redraw this over here. So how will we draw resonance structures from this thing? Well, if you can't push electrons to something, right, try going the opposite direction. Let's see if we can push this lone pair into other parts of the molecule. Yeah, it turns out we can. So we take this right here, we move this onto here. I apologize if it's kind of bulky, but if you can kind of look very carefully, these electrons right here are going to go into this bond. Yeah. But if we just said, okay, that's the only arrow we need to draw, we'd run into the same exact problem that we'd have over here, right? Because this right, has an H here. And if we move that, move this bond right here, move this lone pair into this bond right here, what would happen is that you'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'd be violating the octet rule once more. So we can't do that. So what's going to happen here? Now, pay very close attention because while this gets intuitive as time goes on, if this is your first time seeing this or your first time actually sitting down and like wrestling with the content, then this might be a little confusing. So what's going to happen is that, well, what happens if you, I don't know, move into a house that's already at capacity, or move into a house where, four people live already, and there can't be more than four people living there? Well, you gotta kick someone out, right? And so unfortunately, um, unlike humans and their laws regarding tenants and things of that nature, molecules don't really care that much when it comes to evictions. And so what ends up happening is that you get this, you take this bond right here. I'll highlight this. Take this bond right here, and you move it onto the adjacent atom. You displace it essentially. And so what ends up happening is that you end up with this. 1, 2, 3, 4, 5, 6. Cool. You end up with this. Alrighty. Let me go ahead. Give me 1 second. Let me color code this so it's kind of easier for you to kind of wrap your heads around, right? So this red guys, so this guy is right here. Yeah, let's do that. Yep. And so just like major resonance pattern 1, right? Once you get rid of a charge somewhere, the charge has to pop up somewhere else. And the charge popped up right here. Oh, and be very careful of this as well, right? But I almost forgot to draw this here. This is also a very common mistake, right? Is that when you're doing resonance, when you're switching between structures, sometimes people forget parts of your structures. You forget a bond, you forget a lone pair here and there. It depends. But anyways, so this happens. Yeah. And hopefully, I'll give you a second to kind of absorb this. Pause the video if you need to. But you have a lone pair. The lone pair goes into a bond, and then in response, something else pops off somewhere and is displaced in order to make room for the other lone pair. So the best way that I like to summarize the structure, this major resonance pattern 2, right, is that when you ever have a situation where you have a bunch of negative charges, right, or you have to start off by the resonance structure by pushing from starting from a lone pair instead of starting from a plus charge and then moving things to the plus charge. What's going to end up what's going to end up happening is that you are going to basically start moving the electrons from bond to atom, bond to atom. This is generally, right, the case most of the time. There's some weird exceptions, but I'm not here to teach you all the million weird exceptions. So, as you can see here, right, this lone pair right here started off from a bond. This started off from an atom. Yes, this is an atom, carbon right here, and it went to a bond over here. This bond starts off from a bond, right? This resonance move right here, this arrow starts off from a bond, and then moves to an atom. Kind of see that there, right? And if you like, you can pause the video right now and try to figure out what the next resonance structure would be. Okay, so to do that, right, what would the next resonance structure be? Well, we went from bond to atom, then atom to bond, right? And now we're here. So what's going to happen is that I'll draw this in red so it's a little more clear. This guy right here, you know what? Let me. I am the king of running out of room. You'll see this. You'll see this. You'll see this very. It's very apparent once you see me actually teach in person, because I constantly run out of room on the board, which is really rough. So while you're waiting for me to kind of fix everything, oh, and I drew the structure wrong. I just realized I just need one carbon there. Let's do that. Yeah. So I'll delete this right here. Yeah. And then I will fix this right here. So this is going to go to, right? This is starting off from an atom. This atom is going to go into this bond. And in response, this bond right here that starts off with a bond will pop off onto an atom. And so you'll end up with something along the lines of this. This is your red right here. Yep. So the major thing that you have to take away, right, is going from atom to bond, and then right all the way back around again. Bond to atom, atom to bond. Yeah. So hopefully that's a little clear. And also another thing, important thing to remember here as well, right, is if you move electrons, I'm running out of room again. Something must be displaced. Yeah. As you can see here, right? You start off with an atom, right? These lone pairs are on an atom. They move into the bond. And in response, something else goes from bond to atom and is displaced. So these are the two major resonance patterns. Yeah. To kind of do some more practice, right? Totally forgot about the structure over here. I'm so sorry, buddy. Right. But there are also very, very interesting ways to start off different types of resonance structures. Now, obviously, this is a little bit more difficult because you don't have a plus charge or a negative charge overtly in front of you to start off with. So you don't know exactly which pattern to start off with. However, if you would like, let's go ahead and let's pause the video right here and you guys can figure it out. Try it for yourself. Okay, cool. So the way this would work, right? How exactly would we draw resonance structures from this? Well, everyone here hopefully understands that some major non what's it non non-metal elements such as oxygen, fluorine, nitrogen, sulfur, just to name a few, right? Basically, the whole right side of the periodic table are very electronegative. Electronegative, especially compared to carbon. Yeah. What does electronegative mean? Well, just likes to suck up electrons like a vacuum. Yeah. So what ends up happening is that we recognize that, okay, this is an oxygen. What does it mean by suck up electrons? Right. And so what's going to happen is that you see that this is a C double bond O. Yeah. The C is right here, double bonded to an O. And what oxygen will do is that it will scoop up these electrons right here. And what will end up happening is that this oxygen right here, yeah, will basically gain another lone pair and it will become negatively charged. Yeah. And in response, it'll form a plus charge right here. And if you're confused about that on this carbon, if you're confused about that, right? Remember this carbon was fully substituted. 1, 2, 3, 4, fully neutral. But then you all of a sudden you took away one of its bonds and now it's angry, it's positively charged. And based off of this, hopefully you'll be able to figure out what major resonance pattern will happen next, right? Major resonance pattern one will happen. So we'll move on to here. You move on to here. Yep. And you end up with a plus charge right here. Yeah. So let's do some more practice down here. So I just realized this is this is almost the exact same, right? But hopefully you're able to do this, right? Sometimes you also see that the lone pairs aren't strictly like written down for you to see. They aren't obvious to you. But hopefully at this point in your brief career in organic chemistry and chemistry in general, you would know that we don't chemists don't always draw the lone pairs in all the time. So this oxygen is going to have two lone pairs right here. So if you guys would like, you can pause. But for me, I'm going to move this onto here, right? That's the first pattern that's going to pop up. This will reveal plus charge right here, going into major resonance pattern one. Oop, and I realized this is the wrong arrow. I just love double-sided arrows. Plus charge right here, moves onto here, and then the last structure should be this. Plus charge right there. Yeah. Now this resonance structure over here is a little bit different, but you guys can go ahead and do the same thing, pause, and try to figure out yourself. But we'll start off with this lone pair right here. Now, what can we do from here? Well, I can't really pull plus charge, do anything that would cause immediate plus charge. But what I can do is I could do this, move this lone pair right here onto this bond right here, and then this pops off in response. This is major resonance pattern 2. There's going to be lots and lots of different permutations. Sometimes you'll switch between patterns. Okay. Now, before I do anything else, please pause the video, right, and figure out the mistake that I made here. Okay. Hopefully you paused the video, given it some thought, right? But if I just kept on going, I would end up getting, I think, maybe half a point off because I forgot that there's a plus charge formed here. If you saw one of my first videos about formal charge, you have to understand that if you do not account for all the charges that are in your structure when you're doing resonance, when you're doing reactions, you're going to be death by 1,000 cuts. You're going to get minus half a point here, minus half a point here, minus half a point here. So this plus charge is making sure that you keep track of the charge that you generate is very, very important. And that makes sense too, right? Because nitrogen over here was neutrally charged, right? 1, 2, 3, 4, 5, right? Because each of these bonds right here contributes. And now there's only 4 things attached to it. So, 5 minus 4 plus 1. And from here, this fun little lone pair right here is going to go on a fun little trip around this little aryl group. And so this will move onto here, and then this will move onto here. Remember, bond to atom, atom to bond. Yep. And then this moves onto here. This moves onto here. I apologize. Let me just make this a little bit more clear. I write small and somehow I still run out of space. Oh, golly gee. All right, cool. Let me just decrease the size of my font real quick. Cool. So this moves onto here, that moves onto there, and you end up with this major resonance structure at the end. Lit. Okay, cool. So this has basically been your reintroduction or introduction into resonance. But the most important thing that you do from here, this is very, very important. So I want to write it in the biggest font that I can. It's to practice. Take these structures, find some structures on the internet, quiz your friends, just do them over and over again. Make sure that you account for your charges. And with practice, eventually the resonance will kind of tend to click together. And the most important thing also is that you're able to practice and be able to achieve accuracy, but also speed too. You only have 50 minutes to do the exam as of the time of recording this. I don't know if Dr. Ko's extended any of his classes, but without those 50 minutes, then if you are able to do this resonance quickly, then you're going to run out of time. So good luck, good hunting, and hopefully I'll see you guys in the next video.